That's fine, just do it this time. It's fine, all of it's fine. Fine, fine, fine. Please raise your hand so I can see at least one hand and preferably more for who's eating with me at College 910 after class. So I have some people to eat with, cool. Hey, by the way, if you get out early and you're one of the people that was going to eat with us and you want to like get there and see if you can find a table for us, I think that'd be great. Now you just have to wave like mad when you see us because unfortunately context is important and there was a lot of hands over there and I've never seen any of you people before. Yeah, oh, okay, a couple of you look familiar. Okay. But the thing is, the further back you are, I actually should be wearing glasses, but I'm afraid my glasses are like hundreds and hundreds of dollars and I got them kind of scratched such that they annoy the crap out of me and so I don't wear them. Has anybody else ever maybe sort of should have worn glasses but doesn't because they're annoying? Also in the rain, glasses in the rain, holy suck. Okay. Hey guys, you want to talk to me about the harmonic series? I'm only talking about the harmonic series to a totally quiet hall. Man, I came in here with a guy before him, he was lecturing. I felt so bad for him that it was like, he might not as well been up here. It was like hum, 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 and he was up here saying, well, okay, but, huh? And like he was up here begging for attention and not getting it. And I felt like walking up and saying, man, you know, you got to man up. My mic. Is my mic on? Okay, it's on. Okay, what do we got? Stuff. Brain dead recipe. Brain dead recipe, very important. No, okay, your inductive hypothesis should look exactly like what you're trying to prove, except that everywhere you had k, you replace it with k plus 1. Or everywhere you had n, you replace it with n plus 1. I don't care what you name your variable. You can name it Brianna. Brianna, you get to be the variable of induction today. Okay, or we haven't done that yet, but it turns out there are times when the proof is actually a lot simpler if you assume k minus 1 and prove k. Like the math just turns out to be nicer. And that would mean you also do it by assuming Brianna minus 1 and proving Brianna. Either way. Okay, so LHS is left-hand side, RHS is right-hand side. Once you can handle your inductive step, if you go back and read this from your book, it's actually really complete. I mean, it includes things like write out the words basis step. Man, they're really telling you what to do. That actually is what you need to do. I was going to do this fine inductive proof, but you guys seem to want to do the harmonic series diverges. I'm going to do this reasonably fast. It's not that I don't want you to ask questions, it's just that if it's something I feel like I've spent for freaking ever on, I might not go into it too much. Okay, in order to prove the harmonic series diverges, I proved a lemma that was incredibly helpful. And if you haven't been paying attention to what the harmonic series is, the fact that I even want to prove this lemma is going to be very mysterious. So I'm sorry, you have to have at least paid some attention on Wednesday for this to make any sense. So the summation from I equals k sub n plus 1, that's, the subscript is n, and then that whole thing, 1 is added to it. Sometimes people have trouble distinguishing between k sub n plus 1 and k sub n plus 1. This is k sub n plus 1, and up here we're going to put 4k in. Several people have asked me, how do I know that you're adding up 3k sub n times? Well, you're going through it the same number of times as you would if you started from 1 and went to 3kn. How do I know that? Just subtract kn from top and bottom. Just like the distance between 1 and 10 is 10, the same as the distance between 31 and 40 is 10. The same as the difference 1,071 and 1,080 is 10, right? You can subtract off common elements, and it'll tell you how many. The difference between two numbers remains the same, even if you subtract the same number from top and bottom, right? Check 1. Does everybody understand why we're going through this loop 3kn times? Okay. But, in fact, I'm not going to go through that loop 3kn times, because it turns out we're going to use an estimation method. We're going to add up the smallest thing that's ever added up and multiply that by how many times you're going to add up shit. I swear I'm Betty White. Now, if you, that's the way you estimate something that actually looks like this. You're finding a lower bound. But if instead you break the thing into two pieces, you can actually make it a little bit more accurate if you add up the green area plus green plus the red area. See? It's just a little bit more accurate. So I'm going to take this nice thing and I'm going to break it into two pieces. Why would you have known to do this? You would only know to do this if you spent literally, if I weren't dragging you through this, it would take you hours. I mean, even if I showed you exactly how to prove it, but I didn't do the lemma, you would have to think about it and try it and see, man, I almost made it to 1. What would help me make it to 1? You'd have to mess around with stuff. I thought you motivated it very well on your little write-up, Kyle. So we're going to go from k sub n plus 1 to 2k sub n. And we're going to add that summation from I equals 2k sub n plus 1 to 4k sub n. It's just going to work out well. The first guy, you go through the loop k sub n times, right? Programmers, right? This is a for loop. For I gets k sub n plus 1 to 2k sub n do. So you go through that loop k sub n times, and the smallest thing you ever add up is 2k sub n, right? Okay, and for the other guy, you go through that loop 2k sub n times. Once again, if it confuses you, subtract 2k sub n from top and bottom. So that is, you go through the loop 2k sub n times, and the smallest thing you ever add up is 1 over 4k sub n. So the k sub n's all cancel out, and you have 1/2 plus 2/4, which is 1. And all of this is an inequality. These are lower bounds, so you need to have these guys. The pointy part always points to the smaller thing. Someone came up and was confused about my inequality, and they thought it was pointing the wrong way. Keep in mind, I'm looking at a lower bound, so the pointy part better be pointing at it, because the real number is bigger than that. Like a lot bigger than that. I mean, this is the same as I am taller than an ant. I mean, it's not a very helpful comparison. The real number is way bigger than that. Okay, so now that I know, I'm just going to do the inductive step, because the basis step isn't interesting, and if you haven't studied that, then, you know, what can I say? So we're going to do only the inductive step, and I'm lazy, so I'm going to write IS. So my inductive hypothesis is that the summation from I equals 1 to k sub n of 1 over I is greater than or equal to n. And I'm trying to show, this is the IH, the inductive hypothesis, and I want to show that the summation from I equals 1 to k sub n plus 1, that plus 1 is in the subscript of 1 over I is greater than or equal to n plus 1. And I'm going to further use the fact that before, when we played around and we saw how n grew as you add up more and more elements, that it looks like you have to add up 4 times as many guys to get to the next integer plateau. And so we are going to assume, we didn't prove it, but this assumption is going to allow us to prove it. We're going to assume that k sub n plus 1 is equal to 4 times k sub n. Okay? So we're going to start out using the brain-dead theory from I equals 1 to 4k sub n of 1 over I. That's equal to the summation from I equals 1 to k sub n of 1 over I, plus the summation from I equals k sub n plus 1 to 4k sub n of 1 over I. Let me draw a little line here so it doesn't get in the way. Okay? Everybody okay? Lemma says this has to be greater than or equal to 1. So that means why do I get to do that? I get to do that because of the inductive hypothesis. Why do I get to do this? I get to do this because lemma. Okay? And now we're done. A lot of people ask me why I did the lemma. Why did I do the lemma? The same reason that good code, this is an opinion. In my opinion, the best computer programs, no procedure is more than a screen long. You have to be able to get it all in front of your face. And I'm even talking from times when computer screens were smaller. So you segment your code so that marvelous little helper functions exist, and any particular thing only does an amount of stuff that the average little engineer can comprehend. And I mean me. And I'm, I fluster easily. Yes? You don't know, this is not like one of the laws or axioms or whatever. You actually have to do the lemma to use it.
But like, can you do it like when you're starting this?
You can do it in the middle. Computer programmers, you know how instead of calling a subroutine, you can actually just put all the code of the subroutine right there, mainline code? That's what you're talking about. There's a reason this class is in the computer engineering department. This is specifically the kind of mathematics and the kinds of techniques that you use when you're writing good code. That's the whole point. Do you believe me? Okay. No, you don't have to do it for. You could just say, you could do it after, for example. You could say, and now I'm going to use this marvelous lemma, which I prove below. It's very common in math books. You mathy people, I bet you've seen this. That's you, Kyle. You're reading a math book, and it uses some lemma, and there's a footnote, and then there's this incredibly complicated theorem in the footnote. Fuck them. I hate it when they put the complicated stuff in the footnote. Yes? What?
Is it the first one instead of the substrate of the k or not? Is it a k sub n plus 1 or is it k sub n plus 1?
It's k sub n plus, k sub n, the quantity, plus 1. And I would, if the answer had been something else, it would have been clear. I would have said k sub n plus 1, as opposed to k sub n plus 1. See, you need dance for mathematics, right? Did you need to do it as a separate lemma? You do not. You could do it as a straight line code. Yes, Jackie? Because you're using this estimation technique with the little boxes. It's really less than and not less than or equal to. But if you are less tall than me, you are also less than or equal. Your height is also less than or equal to me. It's not wrong for me to say less than or equal, but it's also not wrong for me to say less than. Joe. Joe, you're going to have to ask me after. I've never once understood something you asked in lecture. I don't understand why. You need to sit in the front next time. You sit in the front and I'll have some chance of understanding you. Besides, you should all sit in the front. It bothers me. I know I've seen the guy in the very back rubbing his hair. I've seen you around basket, but I had no idea you were in my class. It bothers me that I don't know you people. I'm not mean. Okay. Let's talk about why induction is a valid method of proof. Let's do a proof by contradiction. We did this before, but I'm hoping it will make more sense to you now. Okay, so when you do a proof by induction, what you're trying to prove is that for all n, P of n is true. That's what you're trying to prove. Well, so what this proof is about is it possible to do a proof by induction involving a basis step and an inductive step according to the rules we've set up in this class, and there still be some value of a natural number where P did not hold? That's the definition of it not being true, that for all n, P of n. Are we following so far? Okay, so let's assume that you did a valid proof, a valid inductive proof, and yet there exists some number of integer values for which P does not hold. So let's take all those values for which P does not hold and put them in a set. Because of the well-ordering principle, there has to be a minimum element of that set. Because we explicitly did the basis step, the minimum element is not the same as the element you did the basis step for. It has to be at least one more. So what that means is that P of, say, let's pick a variable. Today we're using Brianna. P of Brianna, according to our assumption, is false. But we know that P of Brianna minus 1 is true. First of all, because Brianna was the minimum element, and we know we can go back at least 1 because we know there is an element less than that we've explicitly proven as part of the basis step. So that means you now have P of Brianna minus 1 implies P of Brianna. That is a false statement, because anytime you have a statement that evaluates to true implies a value that a variable that evaluates to false, that is a false statement. That means it's a contradiction. I know you guys aren't used to doing proofs by contradiction, and you haven't spent enough time writing proofs. I'm trying to get you time writing proofs. I need just a tiny bit of time to rant. They need to make it so when you guys take your online classes that they make you actually use pens and paper. I don't care if it's electronic paper. I mean, if you use a stylus and write on your iPad or your Surface Pro, I'm great. But there's things that you learn. I mean, in my opinion, learning math is like learning to skateboard. You need to use your body. I mean, they've studied this. It's not just what I think. When you actually put your hand and write things, it makes a connection between your body and your brain such that it moves it into long-term memory. And let's face it, I've been teaching for a long time. For short term, I can teach you guys anything I know. The question is, will you retain it? Average person needs to have that moment of understanding 4 times for a truly new concept. So you need to actually use your body. And I know professors say this all the time, but I really think it's true this time. This mass of people has less mathematical sophistication than previous years before we had online classes. And it's not that I think online classes are evil. I just think you're not spending enough time getting your body involved. Do actual proofs by hand when you can, guys. Anyway, does that vaguely make sense? It has to be a valid method of proof because otherwise, because of the well-ordering principle, you come up with a contradiction because you have P of a number that is true implying P of a number that is false, and that is a contradiction. Contradiction just means false. That's all it means. Tautology means true. Contradiction means false. Okay, so guess where we are now? Strong induction. And with little Mimi dude. He's one of my favorite memes. I like him. I didn't mean, not him. He's just impressed, you know. Okay, so here's the deal. until now, all of our proofs by induction, you're not leaving, are you? Okay. You have to have an actual seat, by the way, by the time the quiz happens. I just want to thank you guys for making it easy for us to use the ante room here. I really appreciate you're not going out that way. There's all sorts of things that when people are kind, things just work better, and I appreciate cooperation. It's nice. Up until now, all of our proofs by induction have had a single basis step. And then we assume P of k and prove P of k plus 1. Fibonacci numbers mess that up. Fibonacci, seriously cool dude. You could write, people have written PhD theses about the Fibonacci series. It's amazing. It brings you the golden ratio. It gives you mutually prime adjacent numbers. It's just, it's a incredibly cool thing. The more things you learn about Fibonacci series, I mean, I'm pretty sure that someone who knew a lot about Fibonacci's could walk in here and tell me something right now that would make me go, whoa. Because there just seems to be an ever-growing list of incredibly cool things about Fibonacci numbers. Yes? My finger is Fibonacci? Oh, cool. Oh, wait, come up here. Tell him. Turn around.
Hi, your finger is also Fibonacci. Like, from each joint, it gets longer and longer. Eventually, it gets to your wrist. So.
Wait, no. Show him the numbers slowly.
Wait, what number?
Explain the numbers. Your finger is Fibonacci. Show it.
I don't know how to explain.
Okay. Well, anyway. Okay. So the Fibonacci sequence goes like this. Your first number is 0. Your second number is 1. Sometimes it's defined that the first two numbers are 1. One thing you need to be careful about is there are slightly different, completely consistent definitions of the Fibonacci numbers that lead to proofs don't work in one system. Proofs that work in one system cannot be transferred to the other without changing some indices, so be careful. So Fibonacci of any Fibonacci number is the sum of the previous two, except you can't say that for Fibonacci of 1, right? There is no Fibonacci of -1. There's Fibonacci of 0 and there's Fibonacci of 1. Fibonacci of 0 and Fibonacci of 1 are your basis elements. So you have to define two basis elements because it takes the two previous ones. So if I came up with a new sequence that was f of n is equal to 3 times f of n minus 1 plus 7 times f of n minus 10, you would need 10 basis elements. Basically, you have to be guaranteed that you have solid numbers for all the guys before you that you need. Does that make sense? You need as many basis elements as the length backward you have to go to define your nth element. Okay, so we want to prove that Fibonacci of n is less than 2 to the n for all natural numbers. It sure looks like it's true. Here's all the Fibonacci numbers. Here's all the powers of 2 that line up to it. Looks like it's true. But we are not happy saying it looks like it's true in math, right? We are going to come up with an inescapably rigorous argument that every mathematician at UC Santa Cruz would look at and say, well, yeah, of course, right? That's what we're doing. That's what a proof is. Okay, so you start off trying to do a standard brain-dead proof, and you say, we want to prove that f of n is less than 2 to the n for all natural numbers. For your basis step, you're great. It holds for 0. Awesome. Your inductive step, you say, we get to assume our inductive hypothesis says that the kth Fibonacci number is less than 2 to the k. Then we write down that f of, why did I use k? Well, I defined the inductive hypothesis in k and then I switched to n. That, by the way, is sloppy, guys. I'm sorry. K. Let me put a K there, and a K there, and a K there. Okay? I know this is a little messy, but everybody see what I did? Say that again? Oh, yeah. Okay. So I'm trying to follow the brain dead theorem. I write down the K plus 1th Fibonacci number, and I say that it's equal to the two previous. That's great. I can replace f of K with 2 to the K. Ooh, man, I did a really rotten job of writing that K on top of that N, huh? How's that? Is that better? Okay. So, but I don't have a rule for f of K minus 1. It seems like I should be able to replace f of K minus 1 with 2 to the K minus 1, right? You can, because strong induction says you don't just assume that P holds for one value when you prove it for the next. It says P holds for everything up to the last little value you're trying to prove. So what I'm telling you is that every proof you've done until now is basically a strong induction proof. You just didn't use anything but knowledge about one value of n that P held for. It just means you get more things to assume. And in fact, once you get used to induction, the standard thing to do is to just always assume all proofs are strong induction. And you just use the values of P that you needed to assume if you need them. Okay? So according to that, if you write your inductive hypothesis like this, you say, hey, f of K, oh, I see why I switched to n. Never mind. Okay, f of K holds, and f of K minus 1 holds, and f of K minus 2, and so on, all the way down to f of 0. Does everybody see? You just assume that that all of those are less than 2 to the whatever. I should have written P of K and not f of K. Yes? That's just the definition of Fibonacci numbers. It's just a rule. It says, hey, we have this new cool thing. It's called a Fibonacci number. It's a sequence, and it is defined by, let's start with 0 and 1, and then from then on, you just always add up the last two. So we start out with 0 and 1. 0 and 1 together is 1, so the next element is 1. 1 and 1 together is 2, so the next element is 2. 2 and 1 is 3, so the next element is 3. 3 and 2 is 5, so the next element is 5. Now it makes sense? Jackie?
I was wondering, in the textbook, there's written as f of n equal to f of n minus 1 plus.
Oh, yeah, that's a good question. Let us point this out. Okay, so this is basically a question of mathematical sophistication. Not that you should be comfortable with it until you've seen it. We define Fibonacci, and by the way, we often write Fibonacci like this. It's equal to f of n minus 1 plus f of n minus 2. It's also common to write it f of n equals f of n minus 1 plus f of n minus 2. Please use this version if you're posting on the forum, because the forum is not very good at subscripts. Use the parentheses like you're calling a function. We're computer programmers, right? Let's call a function. But what that means is, what is f of n plus 2? It's equal to the two previous Fibonacci numbers. What are the two previous Fibonacci numbers? F of n minus 1 plus f of n. F of n plus 1, sorry. Doesn't matter. Also, you can remember algebra back in high school? What that means is that f of n plus 2 minus f of n is equal to f of n plus 1. Why? Because I took one of those bastards and shoved him over to the other side of the equation, like we do sometimes in math, because we're brutal and bullying. Okay? See? How many of you have ever watched Community? Good Lord, I've been binging on Community episodes. And I just saw the one where they bully people with foosball table. Anyway, so I'm thinking about bullying. Did I answer your question, Jackie? Okay. So So that means, because my inductive hypothesis has become multifaceted now, so I can say that f of k is equal to f of k plus 1 is equal to f of k plus f of k minus 1, and that means that that thing is less than 2 to the k plus 2 to the k minus 1. Right? Okay, remember, what do we want? We want to end up, our thing we're heading for, if we do the right thing, we want this to be 2 to the k plus 2. Gee, if that 2 to the k minus 1 was a 2 to the k, we'd be done, right? Hey, remember how I taught you guys to deal with inequalities? We're on the big side of the inequality. What is the comparative relationship between 2 to the k minus 1 and 2 to the k? 2 to the k is bigger. It's bigger. It's already a big tumor. So what that means is that because this is an inequality, I could just go ahead and say 2 to the k plus 2 to the k, because this guy is known to be bigger than that guy. And that means 2 to the k plus 2 to the k is 2 times 2 to the k, which is the same as 2 to the k plus 1. Are my TAs here? Yay! Hi, TAs. Okay? Good? Yes?
In this case, do you have two bases?
Yes, and you must have two. Yes. Oh, I didn't plant him in the audience, but I should have. You are feeding into my ego right now. You have to have, when you're doing a strong inductive proof, if you ever require more than one element, you need more than one basis step. So what that means is that you now have basis steps, and you do not only for n equals 0, you do n equals 1. You have to have, so if n is defined in terms of n minus 5, you need 5 basis steps. Sometimes when people are sloppy, they only do one basis step when they really have to do more. Let me tell you, most of the time that's okay and people are just being lazy. But every once in a while, if you miss the basis step, you can do that sexy math stuff where like you divide by 0 and you prove cow is your grandmother or something like that. You know, you've seen those math proofs that prove 3 equals 7 and stuff like that. If you mess up the equivalent of that for inductive proofs is you mess up the basis step, at which point you can prove all horses are gray and things like that. Okay? So yes, thank you for pointing that out. Now, strong induction is awesome. Don't be freaked out by it. Strong induction just means that your inductive hypothesis holds for all the values up to the guy you're proving. That's all it means. Yes?
The last line that you wrote, why is it 2 to the k plus 2?
Because 2 to the k plus 2 to the k is the same thing as 2 times 2 to the k. And 2 to the k is just 2 times 2 plus 2 times 2 k times. And now you have one more k. So now you have 2 times 2 times 2 times 2 k plus 1 times, also known as 2 to the k plus 1. Oh, so you're not asking for understanding, you're asking what planet I'm from. Okay. An extra 2, I was thinking about the extra 2, and somehow or another it moved up into the exponent instead of being multiplied. Okay, are we happy now? I'm deliriously happy. Are we good? Okay.
Formally write an inductive step. That's for not strong induction.
No, this is strong induction because,
That inductive step that's written right there.
yes, it says, okay, I turned everything to k's, but I didn't need to. It said, hey, that's what that thing says. It says, remember P, I'm going to erase all this stuff. It's going to freak you out. Here we go. P of k is equal to Fibonacci of k is less than 2 to the k. And what they're saying is all values of k up to and including n, you get to assume it holds. That's what this says right here. See? How do people teach without being able to write on their PowerPoint? I do not understand it.
They have big whiteboards.
Modern technology scares them.
If you told me I couldn't teach with my Surface, I would cry.
So like if the computer just break down, all of a sudden you just get kept on.
But it's really not that hard to make me cry. You can show me pictures of puppies being kicked and I'm gone.
So you have that, but you said in this class you throw chalk.
Oh, well, there's chalk here. I can throw chalk at you anyway. I hit the guy behind you. He didn't notice, though. Okay, I can tell. Okay. I have now at least demoed strong induction, so you can do the problems in 5.3 for real now, okay? We're going to spend a lot of time talking about recurrences, and I can tell you guys want to get right to the quiz.